Welcome, my friends. This will be my final video proving trigonometric identities, and any of the identities that we have talked about so far could be used. Let's try to prove that 1 over 2 times the cotangent of x times 1 minus cosine squared of x is equal to cosecant of 2x. Let's start with the left-hand side. You should recognize that 1 minus cosine squared is an algebraic manipulation of the Pythagorean identity sine squared plus cosine squared equals 1. I always remember that 1 minus sine squared or cosine squared is always equal to the other one, so 1 minus cosine squared is the same thing as sine squared. So we can replace 1 minus cosine squared with sine squared in our problem. Next, I know that cotangent of x is the same thing as cosine of x divided by sine of x by the quotient identity. So I can write this as 1 divided by 2 times cosine of x over sine of x times sine squared of x. The reason I use this identity is because now I have sine squared over sine x, and one of the signs will cancel. I'll be left with 1 divided by 2 times the cosine of x times sine of x. Now hopefully you recognize the denominator as the double angle identity for sine. Sine of 2x is the same thing as 2 times the sine of x times cosine of x. We can replace this with 1 over sine of 2x. Our goal is to get cosecant of 2x, and we basically have it. 1 over sine of x is the same thing as cosecant of x, so that means that cosecant of 2x is the same thing as 1 over sine of 2x. We have completed our proof. Let's try another one. We are asked to prove 2 over cotangent of x plus tangent of x is equal to sine of 2x. Let's start to work with the left-hand side. It might not be super clear what we should do first. Let's try converting cotangent and tangent into sines and cosines. Cotangent is the same thing as cosine over sine, and tangent is the same thing as sine over cosine by the quotient identities. We have 2 over cosine of x divided by sine of x plus sine of x over cosine of x. Let's try to get a common denominator between the two terms in the denominator. The common denominator will be sine of x times cosine of x. So let's multiply each term by what it is missing in the common denominator divided by itself. So we must multiply cosine of x over sine of x by cosine of x over cosine of x, and sine of x over cosine of x by sine of x over sine of x. The result will be 2 over cosine squared of x, since cosine times cosine is cosine squared, divided by the common denominator of sine x times cosine x, plus sine squared of x, because sine of x times sine of x is sine squared of x, divided by the common denominator of sine of x times cosine of x. If we combine the terms in the denominator, we have 2 divided by cosine squared plus sine squared divided by sine times cosine. We justify all of this by getting a common denominator and then combining the fractions. Hopefully you recognize that cosine squared plus sine squared is just equal to 1 by the Pythagorean identity. So we can replace that with 1 in our problem. We have 2 divided by 1 divided by sine of x times cosine of x. We can reciprocate the denominator and multiply so that we have 2 times sine of x times cosine of x divided by 1. This becomes 2 times sine of x times cosine of x. We justify the last few steps by reciprocating, multiplying, and simplifying, all related to algebra. Now hopefully you recognize that 2 times the sine of x times cosine of x is equal to sine of 2x, the same double angle identity that we used in the previous problem. That's exactly what we were trying to find. We have proved that 2 over cotangent of x plus tangent of x is equal to sine of 2x. Let's try another one. We have tangent squared of x divided by secant of x minus 1, all squared, is equal to secant of x plus 1 divided by secant of x minus 1. Again, it might be unclear what we should do first. Sometimes you just have to try something and see if it works. If we are working with the left-hand side, we know on the numerator we have a squared trig function. The Pythagorean identities relate to squared trig functions. Specifically, 1 plus tangent squared of x is equal to secant squared of x. That means tangent squared of x, which is what we have in the numerator, is the same thing as secant squared of x minus 1. So we can replace tangent squared of x with secant squared of x minus 1 in the numerator. Now it might appear that something in our numerator and something in our denominator would cancel, but the terms are not quite equal. We have secant squared minus 1 and secant of x minus 1 all squared. Now the trick here is to recognize that the numerator is a difference of squares. We have something squared minus something else squared. Notably, we have secant squared minus 1 squared, where 1 squared is just 1. If you have the difference of squares, that can be factored as a plus b times a minus b. So that means we can factor secant squared minus 1 to secant of x plus 1 times secant of x minus 1. Now we do have a cancellation. Secant of x minus 1 divided by secant of x minus 1 squared cancels the square with one of the factors in the numerator. We are left with secant of x plus 1 divided by secant of x minus 1. At this stage, we have completed our proof. Let's try to prove that cosecant squared of x times tangent of x minus tangent of x is equal to cotangent of x. I'm seeing the tangent of x in each of my terms, so perhaps I would like to factor that out. Now in parentheses, I have cosecant squared minus 1. We have a squared trigonometric function, which must be related to some Pythagorean identity. The identity is 1 plus cotangent squared is equal to cosecant squared. If you solve this for cotangent squared, you get that cotangent squared is equal to cosecant squared minus 1. We have cosecant squared minus 1 in our problem, so we can substitute in cotangent squared. We have tangent of x times cotangent squared of x. We know that tangent is the same thing as 1 divided by cotangent, by the reciprocal identity. That allows us to cancel one of the cotangents. We are left with just cotangent of x, which is exactly what we wanted. We have completed our proof. Let's try another problem. We are asked to prove the identity cosecant of x minus sine of x is equal to cotangent of x times cosine of x. Let's start working with the left-hand side. It might be unclear what we should do first. I do notice that our final answer must be two terms multiplied together. Maybe it would be a good idea to combine our two terms in some way, and the way we can do that is by getting a common denominator. Let's first convert cosecant to 1 over sine using the reciprocal identity. We have 1 over sine of x minus sine of x. If we want a common denominator to combine our terms, we must multiply sine of x by sine of x over itself. Then we will have 1 over sine of x minus sine squared of x, since sine of x times itself is sine squared of x, divided by sine of x. Now both of our terms have a common denominator. When we combine the numerators, we get 1 minus sine squared divided by sine. We justify those steps by algebra, first getting a common denominator and then combining our fractions. Now, I really hope that you recognize the numerator as a Pythagorean identity. 1 minus either sine squared or cosine squared always gives you the other one. So 1 minus sine squared is the same thing as cosine squared. We can replace 1 minus sine squared with cosine squared in our problem. Now, if we look at our final goal, we would like to have cotangent of x times cosine of x. Cotangent is cosine over sine, so let's split off one of the cosines so that we have cosine of x times cosine of x divided by sine of x. Cosine squared is just the same thing as cosine times cosine, so this is a legal move. Cosine over sine is the same thing as cotangent, so we have cotangent of x times cosine of x by the quotient identity. At this stage, we have finished our proof. We have shown that cosecant minus sine is the same thing as cotangent times cosine. Let's try another one. We are asked to prove that 1 over cotangent plus 1 plus 1 over tangent plus 1 is equal to 1. Now, if you're not sure what to do, typically a good strategy is to find a common denominator between your two terms. The common denominator will be the product of our two denominators. So let's multiply each term by what is missing over itself in the common denominator. Cotangent of x plus 1 is missing tangent of x plus 1, so we must multiply by tangent of x plus 1 over itself. This is allowed because we are simply multiplying by 1. Tangent of x plus 1 over itself is just a fancy form of 1. It won't change the actual value of our expression. On the other side, we are missing cotangent of x plus 1 in the common denominator, so let's multiply this term by cotangent of x plus 1 over itself. When we distribute, we will get tangent of x plus 1 plus cotangent of x plus 1 divided by the common denominator of tangent of x plus 1 times cotangent of x plus 1. Take a moment to make sure you understand how I got from this step to this step. Okay, from here we can combine some things in the numerator. 1 plus 1 is 2, so we have tangent of x plus cotangent of x plus 2. In the denominator, we can FOIL everything out. Tangent times cotangent is tangent times cotangent. Tangent times 1 is just tangent. 1 times cotangent is cotangent. And 1 times 1 is just 1. We justify all of this by algebra, getting a common denominator and simplifying. Tangent and cotangent are reciprocals, so they will cancel each other out. Tangent is the same thing as 1 over cotangent. So let's replace tangent with 1 over cotangent. The 1 over cotangent and the cotangent will cancel each other. We will be left with tangent of x plus cotangent of x plus 2 divided by 1 plus tangent of x plus cotangent of x plus 1. We can combine the 1's in the denominator. We will have tangent of x plus cotangent of x plus 2, the same thing we had in the numerator as before, divided by tangent of x plus cotangent of x plus 2 after we combine the 1's. Since we have the exact same thing in the numerator and denominator, the result is 1. We justify this last step by algebra, simplification. We have finished our proof. We have shown that the left-hand side is equal to the right-hand side. Alright, let's try another problem. We are asked to prove tangent of x minus cotangent of x divided by tangent of x plus cotangent of x is equal to 1 minus 2 times cosine squared of x. Again, many of these problems, it might be unclear what your first step should be. If you're unsure, sometimes converting everything into sines and cosines can be helpful. Let's change all the tangents into sine over cosine and all the cotangents into cosine over sine. This is the result. We have sine over cosine for the first tangent minus cosine over sine for the cotangent divided by sine over cosine for the next tangent plus cosine over sine for the final cotangent. Now this is a little bit of a tricky move, but if you multiply the entire expression by sine of x times cosine of x over itself, that will dramatically simplify things. Let's distribute this to each term in the numerator and the denominator. Sine of x times cosine of x times sine of x over cosine of x will give us sine squared of x times cosine of x over cosine of x. The cosines will cancel and we will be left with just sine squared of x. When we multiply by the second term, the sines will cancel and we will be left with just cosine squared of x, but of course we have the subtraction sign in the middle. For this term down here, we will have sine squared of x and then again the cosines will cancel, so we have just sine squared of x. And for the final term, we will have cosine squared of x and the sines again will cancel, so we just have cosine squared of x. We justify this by algebra, multiplying by a unique form of 1. At this stage, you should recognize the denominator as a Pythagorean identity. Sine squared plus cosine squared is equal to 1. So we have sine squared minus cosine squared divided by 1. Now if we look at the final expression we would like to reach, we have 1 minus 2 times cosine squared of x. Perhaps we would like to get rid of the sine squared of x, since our final answer does not have to do with sine. We know that sine squared is the same thing as 1 minus cosine squared by one of the Pythagorean identities. Therefore, we can replace sine squared with 1 minus cosine squared in our problem. We will have 1 minus cosine squared minus cosine squared. This is the same thing as 1 minus 2 cosine squared, since we are subtracting 2 cosine squareds. We justify this with algebra, combining our cosine squared terms. At this point, we have matched the right-hand side, so we are finished with our proof. Let's try to prove 1 divided by 1 minus cosine of x plus 1 minus cosine of x divided by sine squared of x is equal to 2 times the cosecant squared of x. Let's start with the left-hand side. This is another problem where it might be unclear what you should do first. I see a 1 minus cosine of x in the denominator of this term right here. I know that if I multiply by the conjugate of the denominator over itself, that can sometimes help simplify things. Further, I know that the conjugate of 1 minus cosine of x is 1 plus cosine of x. I will end up getting 1 minus cosine squared of x if I multiply by the conjugate. And of course, I know that 1 minus cosine squared of x is equal to sine squared of x. So I'm going to get a common denominator for free if I multiply by the conjugate on the first term. If none of that makes sense, don't worry. Now I'm going to work through exactly what I just described to show you what I mean. if I multiply by the conjugate of the denominator over itself, I will be multiplying by 1 plus cosine of x divided by 1 plus cosine of x. In the numerator, I have just 1 plus cosine of x, and in the denominator, since I am multiplying by conjugates, the two middle terms will cancel each other out in FOIL. I will be left with just 1 minus cosine squared of x. If you need to write out the remaining terms in FOIL, go ahead, but you will see that the middle two terms will be negative cosine of x and positive cosine of x, which would cancel each other out, and we would just be left with 1 minus cosine squared of x. The other term stays the same, as 1 minus cosine of x divided by sine squared of x. We justify this by algebra, multiplying first by a unique form of 1, which was 1 plus cosine of x over itself, and then using the FOIL rule for conjugates. A plus b times a minus b is equal to a squared minus b squared to get 1 minus cosine squared. Now, as I mentioned a moment ago, this is going to give us a Pythagorean identity in the denominator of our first term. You should hopefully recognize that 1 minus cosine squared is the same thing as sine squared. 1 minus either sine squared or cosine squared always gives you the other one, so 1 minus cosine squared is the same thing as sine squared. We have 1 plus cosine divided by sine squared plus 1 minus cosine over sine squared. This is what I was mentioning at the very beginning. Multiplying by the conjugate is going to give us a common denominator, meaning we can combine our fractions. If we combine the fractions, we will have 1 plus cosine of x plus 1 minus cosine of x divided by sine squared of x. We have a positive cosine of x and a negative cosine of x, which will cancel each other out. We will be left with just 2 over sine squared of x. We justify this with combining the fractions and simplifying the numerator, both related to algebra. We are so close to our final answer. We need 2 times cosecant squared of x. But of course, cosecant is the same thing as 1 over sine. We have 1 over sine squared, which is the same thing as cosecant squared. So the final answer will be 2 cosecant squared, which is exactly what we wanted to match. We have finished our proof. Okay, let's look at one final proof. We are asked to prove that tangent of x divided by secant of x plus 1 is equal to secant of x minus 1 divided by tangent of x. We have two terms in our denominator, and one of the most common things that we would do when we have two terms in our denominator is to multiply by the conjugate. The other possible option would be to change secant to 1 over cosine and then to combine the terms in the denominator. Either way could potentially work, but in this case I'm going to multiply by the conjugate of secant of x minus 1 over itself. The reason I like this approach is because I'm looking forward a few steps. I notice that if I multiply by the conjugate of the denominator, I will end up getting secant squared minus 1, since the two middle terms in FOIL will cancel. Secant squared minus 1 is a Pythagorean identity. It's the same thing as tangent squared, and I have a tangent in my numerator, so I know that I'm going to cancel one of my tangents, which is great. So let's work this through so you can see what I mean. On the numerator, we will have tangent of x times secant of x minus 1. I'm not going to be distributing out the numerator. As I just mentioned, I'm probably going to be canceling a tangent in just a minute. We justify this step by algebra, multiplying by a unique form of 1 of secant of x minus 1 over itself, and then using the special rule for FOIL related to conjugates. A plus b times a minus b is equal to a squared minus b squared. I recognize that the denominator is a Pythagorean identity. Tangent squared is equal to secant squared minus 1. So I can replace secant squared minus 1 with tangent squared. As I mentioned at the very beginning, this is going to allow me to cancel one of those tangents. Therefore, I will just have secant of x minus 1 divided by tangent of x by algebra simplification. This is exactly what we wanted, so we have completed our proof. Alright my friends, that finishes this final video of proofs with trigonometric identities.